So sure. The topic of this talk is dispersive estimate of leading order hadronic contribution to muon anomalous magnetic moment, gμ-2, using an up-to-date compilation of total cross-sections, total hadronic cross-sections measured with A plus and minus beams. But just to remind you, where is the pointer? So the letter G stays just for gyromagnetic ratio defined as shown here in this box. It relates the muon spin to its magnetic moment. At a tree level for 1/2 spin particle with unit charge, it's G equals 2 exactly, as prescribed by Dirac equation. Then the deviations from 2 originate from loop diagrams schematically shown here, starting from the lowest order in alpha QED. This is the famous Schwinger term, which contributes alpha over 2 pi. Then there are high order QED contributions schematically sketched here. Now the exact calculations exist up to 5 loops. So this is an outstanding accuracy. This is an example of a quantity which can be computed with a high precision in perturbation theory. Then there are smaller electroweak contributions involving W and Z bosons and Higgs running in the internal loops. And also there are effective vertices connecting 4 photons like this. This effective vertex is dominated by pion, P0 pole. And also there are combinations of diagrams like this one. The experimental situation with G-2 measurement is very good as of now. This is an example of a quantity which experimentally measured with an accuracy better than 1 part per million. And it should be stressed that the accuracy of standard model prediction for the same quantity is of the same order. So it's an excellent benchmark for the standard model and a potential benchmark for new physics beyond standard model. But this somewhat idealized picture is spoiled by when one tries to evaluate loops with quarks and gluons. You see the scale of momentum running in this loop, photon momentum, I mean, is given by the muon mass. So one has to evaluate hadronic polarization operator at q squared of the order of 1 GeV squared, where a perturbative QCD apparently doesn't work. So until recently, the standard method to compute the hadronic vacuum polarization term was to use an optical theorem which relates the imaginary part of polarization operator in the time-like region to the total hadronic cross-section directly measured with electron-positron beams. Also it should be noted that in recent years there was a remarkable progress in lattice QCD calculations of hadronic vacuum polarization. The accuracy was improved and it became comparable to what we get using the dispersion integral. So, but this is definitely beyond the scope of this talk. So we concentrate only on our dispersive estimate. And again, the major contribution to the uncertainty of standard model estimate of G-2 comes from this term, leading order hadronic vacuum polarization. The experimental situation is depicted here. I just reproduce here the two plots by one of the authors from FNAL muon G-2 collaboration, who measured G-2 experimentally in the muon storage ring with 1 ppm accuracy. So the world average dominated by their result, by their measurement, published just recently, maybe 3 months ago, is shown here. So this is the standard model estimate for G-2 divided by 2, as quoted by so-called white paper published by Muon Theory Initiative collaboration in 2020. So there is a 5 sigma tensions between standard model estimate and the experimental value. And here the lattice result is shown, which is somewhat closer to the experiment. Maybe this is just a coincidence, but okay, we'll discuss some implications of this later. The situation with the dispersive estimate somewhat changed when CMD3 collaboration. This is the experiment based in Novosibirsk on Web 2000 collider. Published the new measurements of P plus P minus cross section, which is systematically higher, significantly higher than the same cross section measured by other experiments, and even by their own result obtained before upgrade, when CMD3 was just CMD2. So we'll discuss the implication of new CMD3 measurement a little bit later. And now a few remarks on how the dispersive estimate is performed. We can convert this loop integral to a convenient form shown here. This is the result obtained by Peterman in 1957. So it relates, so this, it explicitly uses the experimentally measured hadronic cross-section in Born approximation, convolved with the integration kernel, shown here. Here we see that the characteristic scale is given by muon mass. S is the squared center of mass energy for this cross section. So we see that the kernel decreases as inverse power of S, which implies that this integral is dominated by the low energy cross sections, namely P plus P minus channel, P0 gamma, 3 pions, and so on. Of course, the Born cross section is not measured directly in the experiment. Here on the on this sketch, I tried to show various processes that contribute to the final state, the observable final state. Of course, there is initial state radiation from electrons. There are loop contributions at the E plus and minus vertex. There are vacuum polarization insertion in the photon propagator. Finally, there will be interference between initial state radiation of photons and final state radiation. And of course,
Люся Русецкая, да, это вот Игоря жена. Она представляет?
Well, this was not a question. To suppress ISR contribution, experimentalists usually apply an explicit veto on additional photons in the final state, but doing this in this manner, they also partially strip off final state radiation, which should contribute to the total cross-section, total Born cross-section. So to obtain Born approximation for the cross-section, we must correct the published cross-section for vacuum polarization, unless the experiment authors didn't do that themselves or did this partially. Then we must add back final state radiation to account for additional photons in the final state, which is a part of the total cross-section. And that's it. We get the we get the total hadronic cross-section and Born approximation as shown here, with the only non-trivial part sitting in the hadronic vertex. There is some form factor. When photon propagator and E plus E minus line are just undressed, are bare. And this is how the dispersive estimate is performed. In practice, what is technically needed to do this estimate? The typical situation is that some hadronic final states, either exclusive like P plus P minus or inclusive at higher energies, are measured by multiple independent experiments with quite dense binning over energy, center of mass energy. So the first step to get the input for dispersive integral is to somehow average, parameterize the cross-section and average multiple experiments and fit our parameterization to multiple experiments. Then there are two essential energy regions where we cannot rely on direct measurements of the cross sections. First of all, this is the region just above hydroproduction threshold, just above P0 mass. The lowest state is just P0 gamma for 1 minus minus quantum numbers. Then double pi and P plus P minus cross section is also measurement starting on the starting only from 300 MeV. This is above the threshold, significantly above the 2 pi threshold. So here we must use some parameterization for the missing part of the cross section. And second region is the high energy region, well above beauty production thresholds, double beauty production, where we can rely on the perturbative QCD parameterization of the total hadronic cross section, which is quite reliable. So I briefly I've just briefly listed the ingredients of our estimate. So on the input, we have a database of total hadronic cross-section. We uniformly rescale them to the so-called hadronic R ratio. The list of input data is given in the backup. It's quite long, so we'll just skip this. Then we must parameterize and fit the R ratio in each hadronic final state. Then we fit the fitted parameterization is substituted in the dispersion integral, and we get our result, our leading order hadronic contribution to G-2. It should be mentioned that all those ingredients were around for 20 years. We participated in the particle data group collaboration, and where we maintained me review on total hadronic cross-section with A plus A minus beams. So the reference to our last contribution to PDG is given here. So having all those things in place, we just decided to utilize our database for something useful. And G-2 is G-2 dispersive estimate is an example of a useful thing that can be obtained for free using our prerequisites. This work is by no means is not original, because first estimates of this kind were made about 40 years ago. There was pioneering work by Edelman and Jäger-Lehner, published in 1995. So ideologically, we do not differ much from other groups making the same estimates, but our estimate is, I think, is not completely useless, because we do not share any common program code with other groups. So our estimate can be considered as an independent cross-check. Concerning the parameterization of the cross-section of the, more precisely of normalized cross-section, normalized to a point like mu plus mu minus cross-section with zero muon mass. As I mentioned, in each final state, the cross-section is measured by many experiments, many independent experiments. So the shape of the cross-section is typically dominated by contributions of various intermediate states like rho meson, omega meson, and so on. So in principle, one can parameterize the cross-section analytically using a set of amplitudes corresponding to those resonances with known masses, widths, phase shifts, and so on. But I guess such a procedure would be justified only if we can use an additional external input to the parameterization, like partial wave analysis and so on. Given only a bare set of total hadronic cross-section measured with E plus E minus beams, we have more precisely, if we restrict ourselves to using only E plus E minus data, all the information is already contained in the measured cross. Looks like we lost sound. So all the necessary information about the cross-section is already there. So we don't need to make any model-dependent parameterization. So we just we just parameterize the cross-section by some continuous piecewise smooth curve. in our case, this is just a piecewise linear curve, and that's it. The only thing to do is to determine an optimum position of nodes of this curve. And this procedure is data-driven. We use a kind of clustering algorithm, which proceeds as follows. First of all, for each value of center of mass energy, we find an energy interval within which the measured cross-section with its experimental uncertainty is compatible with a constant. Then within this interval compatibility with the constant interval denoted by r plus r minus to the left and to the right from the given point. We cluster, we can merge experimental points into a single beam and some weight. In this way, we can define the positions of the nodes of our piecewise linear parameterization of the cross-section. So the algorithm is sketched out textually here. I would just like to mention that one can prove that it always converges, that it's stable with respect to small variations of positions of experimental points, both in energy and in the cross-section value. So the result of such a piecewise linear parameterization of the cross-section in the rho omega interference region is shown here. So our parameterization is shown in by blue line. Whose uncertainty is shown by the thickness of the line. So we see that despite we have multiple measurements of the cross-section with quite fine beams, we arrive at quite smooth parameterization of the cross-section, which uses no prior knowledge of contributions of rho and omega resonances and how they interfere. So this is just an example how the clustering of experimental points works. Then we must fit the cross-section parameterized in this way to the experimental data. Here is the standard chi-squared minimization with the full covariance matrix, which takes into account both covariations between measurements by the same experiment and cross-experiment covariations. There is a quite delicate issue related to the construction of the covariance matrix. If we compute systematic errors entering the covariance matrix directly from individual experiments, we'll get a biased covariance matrix. Qualitatively, it can be explained as follows. So suppose we have two experiments measuring the same section with the same energy, and one experiment is systematically higher than the others, then let us suppose that both experiments independently estimated their relative systematic error to be, say, 2%. Then those points that are systematically higher than the others will get an overestimated systematic error, while the lower experiments which actually underestimate the cross-section systematically will get the lower systematic errors. And this means that the average between them will tend to be lower. It will be attracted by lower points. So this is the bias. And in mathematical statistics, this effect is termed as pertinent puzzle. It's a well-known effect, but its qualitative explanation is just as we try to explain now. Instead of using the individual cross-section measurements to build the covariance matrix, we should use already averaged cross-section to estimate the systematic errors. This makes our problem of finding the mean nonlinear with respect to our parameterization. In principle, this equation could be solved by general method, but it appears that we can resort to a kind of iterative fit. That is, we start from some simple parameterization for the average cross sections. Initially, we can find it ignoring systematic errors. So we at this stage we get overall chi-squared, but just to get some initial approximation for the error ratio to compute the systematic errors, it is just fine. So we can substitute systematic errors into covariance matrix, run the linear fit, extract the fitted value of error ratio, then insert it back into this expression, and so iteratively we arrive at a stable result. On the next slide, this plot shows why we cannot construct covariance matrix naively, as I explained on the previous slide. So if we use systematic errors from individual experiments, the fit will be biased. This is shown by the red curve with the error band. So we see that it's within 1 sigma, it differs from it's lower than the unbiased fit obtained using the procedure outlined on the previous slide. Okay, in the backup, there are more pathological examples of biased fit. I think this is not too interesting. Now moving into results. So we perform this procedure for each hadronic final state, starting from P plus P minus with optional FSR gammas. Then the next by-size contribution is 3 pi in final state, then 4 pi, and so on, so on, so on. Finally, we sum this up to get our estimate for the leading order hadronic contribution to G-2. The first error here is the propagated uncertainty of A plus A minus measurements. Then the second is the uncertainty of our parameterization of the cross-section. And this one, the linear one, is due to uncertainties in radiative corrections. Speaking more precisely, our treatment of radiative corrections. So this result is consistent with what other groups obtain. recently, in 2020, several estimates made by the same method were averaged by the muon theory initiative group. So this is their value with the total error shown here, which is comparable to our. So we see here that even we included some new data, the results are quite consistent. And moreover, we have a good third channel agreement with a relatively recent publication. I give a reference here. Just to facilitate the comparison with other publications, we choose the same integration ranges as they did. So in principle, the result is quite stable with respect to variations of the center of mass energy ranges. So the overall picture of the normalized cross-section is shown here. Here we just reproduced our plots from PDG. The reference is given here. This is the total error ratio, which includes all the inclusive channels, the sum of inclusive channels before in the region from the production threshold, hydroproduction threshold to 2 GeV. This is the blue curve. Then the inclusive measurements made at higher energies are well matched to our sum of exclusive channels. So some charm and beauty regions are shown here, along with QCD parameterizations of the total cross sections. So this is just an illustration. I already mentioned that the situation with cross-section measurements somewhat changed this year when CMD3 collaboration published their measurement of P plus P minus cross-section, which is shown here, which is systematically higher than the others. So locally in the region, in the raw peak region from 600 to 800 MeV, the tension between statistical tension between CMD3 result and earlier measurements is at the level of several sigmas. I just reproduce here the plots from CMD3 paper. The reference is given here. So the yellow band shows their measurement with its uncertainty normalized to unity, and then all the measurements are normalized to CMD3 are shown by different colors. So we see that on top of raw peak there is a 5% disagreement between CMD3 and other experiments. In appendix, I quote a recent talk by CMD3 authors who tried to pin down possible sources of this discrepancy. So they tried to identify sources of systematic uncertainty which could be overlooked and which could contribute to both to the systematic shift between CMD3 measurement published this year and CMD2 result obtained on the same detector before upgrade. So unfortunately, they came to no conclusion, and CMD3 experiment is planning to make several duplicated runs just to study systematics and possibly find the origin of the discrepancy. If they confirm the results, then if they confirm the results, this would imply that there is some systematic problem with other measurements by other experiments. Anyway, we cannot exclude CMT3 data as far as they they were not superseded by something new from CMD3. So we just include them into the fit at cost of normalized chi-square. It's just about 2 in this case. This is a global chi-squared for the fit from the very threshold to GeV. We follow a standard prescription how to deal with fit results if the fit is improbable, if it has a low probability corresponding to high chi-squared. So we just we just inflate the error, the uncertainty of the fit given by the thickness of this green band by a factor of square root of normalized chi-squared. Still, the total experimental uncertainty already scaled with chi-squared remains at sub% level, which is good. If we, for the moment, if we assume that there is no CMD3 experiment, the fit value, the fit will be a bit lower, but still it's compatible with our fit, including new CMD3 data. Of course, one can ask a question: what if CMD3 is correct and other experiments have some systematic bias? So if we perform a fit dominated by CMD3 by excluding other measurements, the result will be somewhat encouraging for latest people. But as I already mentioned, we cannot voluntarily exclude any of the experiments unless they identify possible origins of their systematic biases. The situation in other channels is shown on the next slides. This is P plus, P minus, P0 cross-section dominated by omega and pi meson contributions. So the global chi-squared is not too good here, but we scale the fit uncertainty. Then the next contribution shown here is just P0 gamma final state. Okay, 4 pions. Again, we have problems with the fit here, but as soon as we do not exclude any data, we just scale up the resulting error. Well, this is the high energy region. We just show this plots for reference. Actually, we don't above 12 GeV. We don't use any experimental data. Instead, we are using QCD parameterization of the cross section. So coming to our final result, this is the table just reproduced from the previous slide. Here's our value of linear hadronic contribution to G-2. It's, as I mentioned, it's compatible to the world average, despite we included newer CMD3 data, which are in tension with the others. It should be stressed that even with inclusion of CMD3 data, the tension between standard model prediction for G-2 divided by 2 and its experimental value remains at 5 sigma level. So the problem is not cured by CMD3. So the result of our exercise with the P plus P minus fit performed only with data by CMD3 data is shown here. it drives the standard model prediction of the anomalous magnetic moment. It makes it compatible with the experimental value, but as soon as we have no reasons to prefer CMD3 over other experiments, don't take this too seriously. The lattice-based estimate of the leading order hadronic contribution is also shown here. You see, it has a remarkable accuracy comparable to the dispersive estimates, and it's somewhat closer to the experimental value. Maybe it has some implications. Moving on to conclusion. So once again, here's our dispersive estimate of the leading order hadronic contribution to G-2. It's despite an inclusion of high CMD3 data, it's consistent with estimates made by other groups previously. If we insert our hadronic contribution, leading order hadronic contribution into the standard model estimate for G-2 divided by 2, we still get attention with the experimental value at a level of 5 sigma. So the puzzle remains. Thank you.
Okay, thank you very much for the interesting presentation. Please, questions from Zoom first.
Question. Yes. Oh, of course, I'm understanding that you are not taking into account yet in the analysis of the CMD results, and the question.
Andrei.
Yes, Andrei, got it.
On the contrary, we take into account CMD3 results.
We took. You took.
Yes.
You also took and got what you got result.
Yes, and
we get the similar shift in the hadronic vacuum polarization contribution as the CMD3 results got after substituting. Did you just?
Yes, exactly. Yes, exactly. On the previous slide, okay, let me roll back.
Mm-hmm. So you are confirming their conclusion that
yes.
In their analysis, when you are substituting these new data for the form factor, this is moving the discrepancies with the prediction of the standard model is decreasing.
Yes. Okay. Unfortunately, I cannot roll back to the previous slide. Something.
Okay, this fact understood. So this means that your programs of the are compatible in some sense.
Yes.
Their program and your independently written program of evaluating hadronic vacuum polarization contribution. Okay, fine. And then the question is, in one of your slides, you have shown the cross section, the behavior of the cross section, R ratio in the low energy region, and where you was taking into account the 3-loop results for the R ratio only. But we know, first of all, with UD and S quarks, but we know that now there do exist even the 4-loop results. This is the question. And alpha S in this region is not small. Did you have a look what will be the effect? Including, by the way, including the massive contributions as well, because it is known that in this region, even the S quark, at least for the D function, at least the strange quark massive effects are also very important.
D function, by D function, you mean Adler function?
Yes, yes. So the similar effect we may expect for the expression, for the theoretical expression for the R ratio, but with taking into account threshold contributions and massive effects. Not only massive.
This sounds quite interesting, but well, it follows from your argument that the optical theorem is broken.
No, the optical theorem is not broken. Optical theorems do exist. I mean that these red curve which you have,
we don't use red curve in this region. Sorry, we don't use the red curve in this region. We just use plain data at low energies.
This red curve is just written down just for
yes,
as estimate for the comparison.
Yes, exactly.
And this is not important in your analysis, but those who want to compare this, they may play the game themselves.
Yes, of course. So these plots were prepared for particle data group for the.
And in any case, the question is in fact also appeared because this year at the Lomonosov conference, I heard the talk of the representative of the best three collaboration, which are claiming that in the high energy region, at least in this high energy region, I guess at least, they are getting the result which disagree with the for R ratio with the perturbative QCD prediction. I was really amazed.
So we can we can try to look at the data points. I guess that's three results. Do you mean the region from 2 to charm threshold?
Yes.
So we
first I was really amazed then, and then asked them why, and they were unable to answer the question how many terms in the perturbative QCD prediction they have taken into account, and did they take into account the massive effects as well. So I am not criticizing your analysis, but this is the message of warning, probably maybe to also to the best collaboration and to you if you face these statement in there somewhere and while reading their papers. Okay.
Well, thanks. I think I found the relevant plot. So those three measurements are shown here in red.
Yes.
Not in red. Let me see.
We could leave this subject for further discussion.
Okay, we may discuss later on, or this may be the chance for me to visit Protvino and to discuss with you face to face. Okay.
You're welcome.
Thank you.
Thank you.
Maybe one very short comment or question, please.
Everybody expects this. So I made a remark on one of the slides before the summary. Okay, I cannot scroll again. Can we scroll to conclusion? Next slide. Yeah, previous one and previous one. Well, so I listed some prospects associated with T-channel scattering as well. So there is a project of muon-E experiment at CERN, which dumps the muon beam onto a fixed target and just measures the T-channel muon electron scattering, which can be also used to extract vacuum polarization at low T. So this measurement will be complementary to what we have here, and the muon E, the projected accuracy of muon E experiment is high enough to so the muon E experiment will be accurate enough to get comparable accuracy with the dispersive estimate, which uses the time lag data.
Okay, so
Okay,
you
thank you.
can give a definitive answer.
Okay, thank you. I think we should start the next talk.
Thanks.
I'd like to invite Evgeny Krushin to start his talk.
You hear me well?